So I'm now gone ahead and I've cut the structure at the location of the inflection points. I've already reproduced the free body diagrams here for each of the inflection points, and I want to take a few moments to describe them. First of all, inflection point 1 we found right here at 3L over 13, 2.769 meters from C. I decided to cut right there for inflection point 1 and look at the right-hand side all the way to C. So the free body diagram for it looks like as follows. There is the y and x forces that are expressed here at that inflection point. The reaction, cy, cx, and the moment at C. The distance is 2.769, and the distributed load only over that portion, okay? Because this is the load that's over that distance, not this point load. I've also calculated already what the equivalent point load is for this portion of the distributed load, 12 kilonewtons per meter times 2.769, which is 33.228 kilonewtons. Now, I do the moments at the inflection points, okay? It's the easiest way to ensure that I get these appearing in there. So the sum of the moments at inflection point 1 equals to 0, which gives us, I'm going to go left to right. So the first one is going to be the moment caused by the equivalent point load caused by this, which is that, 33.228 times a distance of half of that, 2.769 divided by 2. And this moment, with respect to this being positive, is negative, because it's clockwise. Then the moment caused by cy with respect to that inflection point is going to be cy times a distance of 2.769. And this moment, with respect to this inflection point, is positive. The moment caused by cx, nil, because the distance, the perpendicular distance between cx and that inflection point is 0. Lastly, the moment at C. This is a moment already. We don't multiply it by a distance. The distance is already baked inside of it. I'm guessing up here that Cm is clockwise. With respect to that, negative. Okay? So look at that. We now have another equation of equilibrium. I could rearrange it to make it look slightly nicer. I'll do it just below here. So I just rearranged it right here. Cy times 2.769 minus Cm equals 46.004. I can't do anything else with this, at least at the moment, so I park it and I call it equation 4. So that's for inflection point 1. Now for inflection point 1, I could have gone to the left-hand side if I so chose. I just chose to do the right-hand side. Okay? Inflection point 2, right here. Okay, at a distance of L over 8 for the intermediate support, or in our case, the corner at B. I sketch it as such, and I chose to go all the way to the support at C. Okay, that way, these same unknowns would appear from here and here as well. Okay, I could have gone the other way, so I could have gone this way. I simply chose to go the right-hand side. So I've already calculated for myself the equivalent point load from the distributed load over the 10.5 meter distance, right? If this is 1.5, then the remainder all the way to C is 10.5, which is 126 kilonewtons. And now I'm going to do the sum of the moments at inflection point 2 and see what kind of equation that gives us. So again, I'm going to go left to right, sum of the moments with respect to this inflection point. I'm going to first figure out the moment caused by this equivalent point load, which is going to be 126 times a distance of 10.5 divided by 2. And this moment is negative with respect to that being our positive. Then the moment caused by Cy, which is Cy times 10.5. This moment is positive. Cx causes no moment with respect to inflection point 2 for the same reason as here. And lastly, the moment at M. This moment is a moment. You don't multiply it by a distance because it's a moment. The distance is already inside of it. Okay? This is already a moment. If you multiply it by a distance, it would be kilonewton meter squared. Make sense? Cm, I'm guessing, is clockwise, therefore negative. Okay? So I'm going to rearrange this a little bit. Voila. Cy times 10.5 minus the moment at C equals 661.5. Last inflection point, right here, at a distance of 3L over 13 with respect to A. So I chose to cut there and look down. I could have looked up if I wanted to. I simply chose to look down. So I bring these reaction forces in it. The free body diagram looks as such. Here's the distance, 1.385. I'm showing the internal X and Y forces at that inflection point that are expressed. And then I'm going to do the sum of the moments with respect to this location. I've also reproduced the 3 reactions at A that we guessed when we did our original free body diagram. So, sum of the moments with respect to this inflection point. What I'm going to do is I'm going to go bottom to top, and I'll do the moment with respect to there. It's going to be AX times a distance of 1.385 meters. Okay? With respect to this inflection point, this is trying to turn in the same direction as that. So this moment is positive. AY causes no moment with respect to this inflection point because AY goes through it. The distance is 0. And then there is AM equals to 0. The moment at A, we guessed it going this way, which is the same as that, so positive. Okay? So what we get, I'm just going to rewrite it slightly nicer. Okay? AX times 1.385 plus AM equals to 0 and 6. So look at this. We now have 6 equations in 6 unknowns. The next step is to solve that. The solution to this, to get each one of these unknowns, is a bit tedious. It's not hard, but it's tedious. Okay? So what I'm going to do is I'm going to let you try that out because practice is how you become awesome at this. I'm going to put the answer to the reactions in the description of this video. As well, I'll link to part 1 of this video that shows us how to get to this point. And I'll link how to do the shear and bending moment diagram for this.